Let's think back to our friend, the square root function. What's the square root of 2? Now, the square root of 2 is about 1.414. What's the square root of 2.01? It's awfully close. It's 1.417 and a bit more, which is really close to the square root of 2. What's the square root of 1.99? Well, it's also really close to the square root of 2. It's 1.410 and a bit more, which is really close to 1.414. The point here is that nearby inputs are producing nearby outputs. Let's try to see these numbers. What does the graph of the square root function look like? Is this the graph of the square root function? Well, take a look at what happens right here. Nearby inputs are not being sent to nearby outputs. Inputs very close to 2, say something a little bit less than 2 and something a little bit bigger than 2, are being sent to outputs that are quite far apart. The numbers show that couldn't have been the graph of the square root function. But what does the graph of the square root function look like? This is what the graph of the square root function looks like. It looks continuous. It's one nice curve. In particular, nearby inputs give rise to nearby outputs. Let's try to capture the concept of continuity. A bit more precisely than just a picture on the graph, here's sort of a moral definition of what I mean when I say f of x is continuous at a. So morally, I mean that inputs near a are being sent to outputs near f of a. From this perspective, it looks like the function f of x equals the square root of x is continuous at 2, because inputs near 2 are being sent to outputs near the square root of 2. How do we make this intuition a little bit more precise? Here is a precise definition. To say that f of x is continuous at a is to say that the limit of f of x as x approaches a is equal to f of a. Now think back to what we mean by limit. To say that the limit of f of x equals f of a is to say that I can make f of x as close to f of a as you like, as long as x is close enough to a. But that's really the spirit of continuity. Continuity is trying to say that nearby inputs are sent to nearby outputs. And this limit statement is capturing that sense. It's saying that I can make the output close to the output at a as long as the input is close to a. This definition's pretty involved. We've got to try to unpack this a bit. So what does it really mean to say that the limit of f of x equals f of a as x approaches a? To make this statement, I really need to know that f of x is defined at the point a. I can't talk about f of a unless I know that a is in the domain of f. To talk about the limit of f of x, I also need to know that the limit of f of x as x approaches a exists. I need this to be some number so I can talk about it being equal to some other number. Well, once I've got these two statements, then it makes sense to claim that the limit of f of x as x approaches a is equal to f of a. But before I can make this third and final statement, I'm really assuming that these two preceding things hold. Right? So the definition of continuity is a little bit more subtle than it seems. It's really these three parts. The function has to be defined at the point, the limit has to exist and be equal to some number, and then I can say that that number, the limit, is equal to the function's value, because it makes sense to talk about the function at that point. Nothing we've done so far really captures the idea that the graph is a single curve, a single continuous curve. We've always just been working at a single point. This is the definition of continuity at the single point A. But often we'll want to talk about continuity on a whole interval at once. So we'll get rid of this, and we'll make this slightly fancier definition. To say that the function is continuous on a whole interval from a to b is to say that for all points c in between a and b, so c is bigger than a and less than b, so c is in the interval a to b, then f of x is continuous at that point c. So this is what we mean when we talk about continuity on a whole interval at once. So that's the definition for open intervals. What about closed intervals? We have to be even a bit more careful when we talk about continuity on a closed interval ab as opposed to the open interval ab. So if we say that the function is continuous on the closed interval from a to b, we mean that f of x is continuous on the open interval from a to b, so in between a and b. But then what happens at a and at b? Well, the limit of f of x as x approaches a from the right-hand side is equal to f of a, and the limit of f of x as x approaches b from the left-hand side is equal to f of b.